Recording is rolling. It's Wednesday, January 7th. We're going to lesson 7-1, graphing exponential function. Oh, hold on. Got a phone call. Let me get that real fast. All right. And we're back. All right, so graphing exponential functions. So guys, exponential functions take a term that we haven't used yet. It's where x, the variable x, is actually in the exponent. Okay. Now it's different from before. You guys remember things like y equals x squared was a parabola, or y equals x cubed could be a cubic shape, right? And these could be classified as polynomials or parts of larger equations that look polynomial, right? But if you see something like this, like some base value to the power of x, for example, y equals 3 to the power of x, that is an exponential. And that's a completely different class of curve, right? Here, I'll show you guys what this looks like on Desmos. Right, so if I bring Desmos over, right, here, I'll do a couple of graphs here. What is y equals x to the power of 3? Now, this is something you guys saw last semester. You guys remember x to the power of 3 looks like that, right? But what is y equals 3 to the power of x look like, right? And that's that blue curve. You guys see that blue curve? Okay. Yeah. If I zoom out, which one do you think is growing faster, the blue or the red? Yeah, it's going to be the blue. Here, I'm going to change this axis system to, let's change this from -5 to 5, like that. Okay, if I do that, yeah, okay. Now look at the scales here. You guys see that x have gone to like 5 here, and the y goes to 500. You guys see that? Right. Yeah, so when you go way out, yeah, that exponential definitely beats the polynomial equation every time. So, right. So these are equations that take off real fast. Right. A common application involves interest on loans or investments. Right, so I'll do that with you guys. This is a simple compounding. I'll do a like a more multiple compounding with you guys. Right? And Alex 717273 is open. It's not due until next Friday, so you guys got plenty of time. Right? But right, I'll do some examples with you guys. Right? Okay, so how could you create that graph? I mean, I just showed you guys on Desmos what the graph looks like. Right here. How about this right here? Y equals 3 to the x. Right. Well, you can always make a table. Right. So remember, just like for every graph you've ever done in this class, if you don't know what the graph looks like, you can always say y equals 3 to the x here. Right. Plot a bunch of points and just see what naturally emerges. Right. Okay, so let's go -2, -1, 0, 1, 2, 3. Okay, so if I plug in -2 for x, isn't that 3 to the power of -2? Okay. And guys, what's 3 to the -2? Is that 1 over 3 to the 2, which is 1 over 9? Is that true? Which is like 0.111. Okay, so this is 1 over 9. Okay. How about what, guys? What's 3 to the -1? Is that 1 over 3? Okay. What is 3 to the power of 0? 1. Yeah, sure is. It's 1. Okay. So here, I'll show you guys on the calculator. 3 to the power of 0 could be just 1. You guys see that, right? Get 1. How about what's 3 to the power of 1? 3 to the 1. Is that 3? What's 3 squared?
9.
9. What's 3 to the power of 3?
27.
27. Ah, okay. So now we got a bunch of coordinates. Okay, we can start making a graphic. Let's go x-axis, y-axis. Okay, it's taking off real fast here. All right, so I'm scaling my axes. Let's go -2, -1, 0, 1, 2, 3. Right, but the y-axis I'm going to truncate. So let's go 10, 20, 30. But 10, 20, 30. All right, and plot some points. So -2, 1, 9. That's like right here. Bam. -1, 1/3. It's like here. Bam. 0, 1. Bam. 1, 3. Bam. 2, 9. Bam. 3, 27. Bam. That's pretty close. Okay. Hey, does that look like that curve on Desmos I just showed you guys? Pretty much. Right? So if you have a base to some power x, it tends to make a curve that looks like that, and it takes off real fast. Yeah.
Sorry, can I go print it down?
Yeah. Go ahead, take that. Okay, guess that. How about right. How about like 3 to the negative x? What would that look like? Y equals 3 to the negative x. Okay. We'll do the same thing. Make a table. So whoops, x, and then y, which is 3 to the negative x in this case. Okay. Let's go -2, -1, 0, 1, 2. Okay. Well, okay, let's start in the middle. Guys, what's 3 to the power of 0? 1. Okay. Now, if I plug in -1 for x, guys, what is -1? It's like +1. And then 3 to the 1 is 3. And then if I plug in -2, -2 makes +2. 3 squared is 9. Okay. 3 to the -1 is 1/3. 3 to the -2 is 1/9. Okay. Okay. So if you have a negative x power, okay, plot this point. So we got 0, 1, 1, 1/3, 2, 1/9. No, label all my axes here, right? But just give you guys the idea of the shape. It's going to basically do something kind of like that, right? Kind of like that, right? Do you see both of these, like 3 to the x and 3 to the negative x? Right? They both have a domain of what? Guys, what's the domain on both of these? What are the possible x values? Could it go to negative infinity and positive infinity? Yeah. So the domain is unrestricted, right? But what about the range? Guys, what about the possible y values? They're only what? Yeah. Yeah, see, only positive, right? It never quite reaches 0. This is horizontal asymptote on both of these curves at 0. Right? And it can be above that, but just nothing below that. That's interesting. Right, so you got that. Right. Okay. Actually, while I'm at it, let's show you guys a couple of bonus posters we have for you guys here. Okay. This one right here is commonly used for uh, radiometric dating, or sometimes you hear carbon dating, right? So if you find an old artifact that's thousands of years old, how old exactly is it, right? Well, there's a certain decay rate of carbon-14. So that right there is an exponential decay curve. Okay? Another common application of exponential growth. Uh, how many guys have heard of Moore's law? You guys know what Moore's law is? It's the number of transistors you can economically fit on a computer chip doubles, I think, every 2 years approximately. Right? Now, this graph, guys, if you stand back and look at this graph, does this graph look pretty linear? Does it look pretty linear? Right. Every point here represents a commercially released chip going from 1970 to 2016. Right. Looks linear. But the catch is, look at the vertical axis. The vertical axis is actually scaled logarithmically. So it goes 1,000, 10,000, 100,000, a million, 10 million. Guess that? Right. If the vertical axis was also scaled linearly, then the graph would actually look exactly like this curve right here. Right? It would actually be exponential. Right? But another example, a couple examples I have to do with you guys involve interest rate. So let's do an interest rate example. Right? And I got a couple equations right here. So we're going to start with a simple example, and I'll do a compounding example. Right? So suppose you invest $1,000 into an account. Okay. And let's say that at let's say 5% interest. Okay. My question might be how much money is in the account after let's say 20 years. 20 years. Right. Right. So say you get $1,000 from first year on the job, you put it into an account that's going to accumulate 5% interest per year, right? And then 20 years later, you check on it, right? How much money's in that account? Okay. So this is going to be exponential growth. And the equation looks like this. The amount that you have as a function of time is equal to the principal amount. Sometimes you see a P, sometimes you see A naught, right? Multiplied by 1 plus the interest rate to the power of, well, the amount of time that's passed. Okay, so P stands for principal. This A is the amount after T time, right? So T number of years, right? this R is the interest rate. You can also similarly use this for like inflation rate or that sort of thing, but we're just going to focus on interest rate now. Okay. Okay. And as T represents the amount of time that's passed. Okay. And in this context, it could be the amount of time in years. So this would be annualized. Right. Although context of the question might be careful about that too. Right. Right. And here's kind of why this. Well, here I'll plug some numbers in, and then you guys, I'll show you guys kind of why this equation takes this format, why this works. Okay. So, guys, what number do you think I'm going to plug in for the principal? What number goes right here? I have three numbers up here. Which is it? 1,000, 5, or 20? What goes right here?
1,000.
1,000. Yeah, $1,000. So I put in $1,000 into the account initially. That's what the principal is right there. Okay. Then times. Okay. Now you guys see 5% interest. That's takes the place of this R. But careful about this, because what is 5% as a decimal? What is 5% as a decimal? Yeah, 0.05, right? Because like 0.5 is half, 0.05 is 5%. Right? It's 5 over 100, isn't that? Isn't it 5%? Same thing as 5%. That's 5 over 100, which is 0.05. Okay. So guys, what's 1 plus 0.05? Is that 1.05? Okay. Now, if you let this money sit in the account for 1 year and it earned 5% interest, then wouldn't you have, well, $1,050, I think it would be. Right? Do you guys see that? Yeah, here, guys, everybody look up here. I want you guys to see why this equation works. Because once you unlock this, then you'll be able to solve a bunch of equations that look just like this. Okay? So if I have $1,000 and multiply by 1.05, okay, I'm going to end up with $1,050 at the end of the first year. Okay? But now that money is sitting in the account at the beginning of the second year, also accumulating interest. So if you ran this for 2 years, can I just say 1.05 squared? And then for 3 years, 1.05 to the power of 3, and so on. Right? Right. How about after 20 years? Can I just put 20 up here? And say there are 20 years that have gone by where I've been compounding, just multiplying by 1.05 over and over and over 20 times. Right? Right. So if I do that, let's see. Guys, take a guess. How much money do you think is in the account? It's earning 5% interest. Right? That's kind of mediocre. Right? For 20 years. How much money do you think at the end of 20 years? The answer is $2,653.30 for that matter. Right. So yeah, so almost triple what you started with just at 5% interest, right? Because again, these exponential curves take off real fast. Okay. All right. So I need to do at least one more example with you guys, which is going to be, what if you have compounding? Okay. All right. So let's do a same number example. So invest $1,000. Let's say the interest rate is 5%, just like before, or 0.05 is a decimal. Right. And let's say the amount of time is 20 years, just like before. Right. But one more detail. Let's say this is compounded monthly. Okay. And what that means is that instead of at the end of the year, it accumulating 5% interest, you take that 5% interest and you divvy it up over 12 months. And then at the end of every month, you get a little bit. Okay. And overall, it's going to result in your account growing a little bit faster. Right? Not a whole lot, but a little bit. Right? And you guys will see how much. Okay. So this equation is going to change a little bit. It's going to go the amount that you have as a function of time is equal to the principal times and then 1 plus. Right. Now, here's where things change a little bit. Instead of just going straight interest rate of 5%, when I take that interest rate, I'm going to divide it into, guys, monthly. How many months are there in a year?
12.
12? I'm going to divide it into 12 parts. I'm going to take my 5% interest, divide it into 12 parts. Okay? Okay. And now it's sort of like it's being compounded every month, or you're earning interest every month. Okay? Now, if I want t to represent the number of years, which I have right here, okay, I do need to multiply that by 12, don't I? Like 12 months in a year times the number of years, right? Or where I put 12, in general, you put in. So this could be NT. That's what I meant to do. But you guys get the idea, right? So if you see an in there, but if it's compounded monthly, you can put 12. Okay. Okay. So say n equals 12. This is like, wow. Okay, you guys get the idea. Okay. So let's do it. So amount as a function of time. Let's take $1,000, put it into account 1 plus 0.05 over 12. Okay. Guys, notice why you divide by 12 is not 1.05, it's just the 0.05 bit. Okay. And then 12 times 20 is the new exponent. Okay. Now, I remember before it was just compounded at the end of every year. I was getting $26.53 in the account. Okay. So I think compounding every month, it's going to be a little bit more than that. It's going to be a little more than 26.53. Let's see what it actually is. So 1,000, the calculator do this, times 1 plus 0.05 on 12 to the power of 12 times 20. Okay. Yeah, look at this. It's $2,712.64. Okay. So it is a little bit more money than before if you compound every month. Right, you guys that? Okay. All right. So if you want to see a bunch more examples in the main video, which is about an hour long, okay, all these green highlighted ones I covered. I think I did an exponential decay here somewhere too. Right? Different kinds of questions they asked, but it's all some versions of these. Right. So for the rest of today, if you guys want to ask me any questions, I can go over and help you out individually. If you want to watch the hour-long video, you can do that. It's on Google Classroom. It's been on a couple of days now. Okay. If you want to hop on Alex and start solving these, you can do that too. And I'm happy to stop by and help you out.